All right, so in this problem, we are given our state of stress. So we're given the state of stress below. So just to remind everyone, our state of stress has 6 unique elements. It has our 3 normal stresses, sigma x, sigma y, and sigma z, and it has our 3 principal stresses, or sorry, 3 shear stresses. Yes?
Dr. Silva, it looks like everybody stopped sharing.
Oh, I'm sorry. Wait. Let me try it again. Okay, can you now see it again?
Yeah, it's back up.
Yeah, thank you for speaking up. So we have the 3 shear stresses. We have tau xy, we have tau zx, and we have tau yz. Okay. So in this problem, it asks us to first verify that one of the principal stresses is sigma p is equal to 30 megapascals. So to do that, what we can do is we can go, we look at our equation sheet here. We can we can use either the matrix form or we can use the algebraic form in order to solve for the principal stresses. So I'm going to use the algebraic form in this case. So let me copy this equation here. All right. All right. So in this equation, we're gonna just plug in the different values that we have from our stress matrix into this equation. Okay. So if we do that, we get sigma p3 or sigma p cubed minus sigma x plus sigma y plus sigma z. So it's just the sum of all the normal stresses. So our only normal stresses are sigma is 10, 0, and 10. So we can so that's going to be equal to 20 times sigma p squared plus our next one is going to be equal to the products of all of our normal stresses minus each of the shear stresses squared, sigma p. So if we plug in all those values, sigma y in this case is 0. So these two terms are going to be 0. So the only term that we have that's non-zero is sigma z times sigma x, which would be equal to 100. All right, and then we'd have tau xy squared, tau yz squared, and tau zx squared. So tau zx in this case is 0. So tau zx squared would be 0, and then tau xy and tau yz are just squared. So so tau xy is 20. So 20 squared equal to 400, and then tau yz squared, which is 10 radical 2 squared, would be equal to 200. Would be equal to minus 200. Okay. All right, and then the last term is equal to the products of all of our normal stresses times 2 times the products of all our shear stresses and plus some other additional terms here. So a lot of these terms are going to have the first 2 terms have a 0 within them, so we can get rid of them. And then we have this term is okay. This term will be 0, and then sigma z tau xy, that will be okay. So we only end up having 2 terms. So we're just going to have minus negative sigma x times tau yz. So sigma x is 10. Tau yz is equal to minus 10 radical 2 squared. And then we have minus sigma z, which is also 10 times tau xy, which is 20 squared. We can set that equal to 0. Right? So if we evaluate all these terms, what we end up getting, a a cubic equation. It looks like this. We get sigma P3 minus 20 sigma squared, sigma P squared, minus 500 sigma P plus 6,000 is equal to 0. Does anyone have any questions so far? Okay. All right. So in this case, we have a cubic equation. So you could find the roots of the cubic equation either using a root solver, or you could graph. You could make a graph of sigma p as your x, and when y would be equal to 0, you would have your roots. But in this case, we were actually given one of the roots of our equation here. Okay, so what we can say is we know that that sigma p. So we can set sigma p equal to 30 megapascals, and we can see whether or not this equation would be true. So we're just going to plug in our 3 values here, or 30 megapascals, into our equation. All right, so if we do that, we would get 2,700 2,700 megapascals cubed minus this would be 18,000 minus 1,500, or 15,000 plus 6,000. Right, so we end up getting 3,300 minus 3,300, or 33,000. So we end up getting 0 does equal 0. Therefore, 30 megapascals would be one of our roots. Okay, so part A of the problem is finished. All right, so then part B of the problem asks to find the remaining principal stresses. So what we can do is we can divide our original polynomial by sigma minus 30, which is one of our principal stresses. So we're basically going to factor out sigma minus 30 to get our 2 remaining principal stresses. So we do our long division. So we do this. What we end up getting is we'll multiply the terms out front by sigma squared. So, and then we'll subtract them. So if you multiply sigma squared by the sigma minus 30 term, we'll end up getting sigma P30 cubed, or sigma P cubed. And then we'll get minus 30 sigma p squared, and then we have to subtract these terms here. So if we do that, what we end up getting is we get 10 sigma p squared minus 500 sigma p plus 6,000. You can repeat this process. So you would do have our second term would be 10 sigma p. You would multiply it out, so we get 10 sigma p minus 300 sigma p, and then we have to subtract both the terms from it. So we end up getting minus 200 sigma p plus 6,000. So we're going to multiply the sigma minus 30 by minus 200. We get minus 200 sigma p plus 6,000. So we end up getting, we have to subtract both terms. So this would end up being 0. All right. So what we'd end up getting is we get sigma minus 30 times sigma squared plus 10 sigma p minus 200 would be equal to 0. Okay. And then it's pretty easy to factor this out, is that sigma minus 30, the second polynomial here would be equal to sigma plus 20, and then sigma minus 10. Okay, so now to be equal to 0. So if we looked at each of these equations separately, we get our 3 principal stresses. So our maximum principal stress would be equal to 30 megapascals. Our second principal stress would be equal to 10 megapascals. And then our minimum principal stress, which is our third principal stress, sigma P3, would be equal to would be equal to minus 20 megapascals. So are there any questions about if you were given one of the principal stresses, how you could then find the other 2 principal stresses?
I don't have a question, but can you just scroll back up to your work up top?
This is Don. You had a question?
Yeah, can you just scroll back up a little bit?
Sure.
In the case of, maybe if this showed up on a quiz, if we were to just graph it and solve for the roots graphically that way, would you still want us to check using like hand calculations similar to this?
I would like to have like some alternate verification that this is correct, or that these principal stresses are correct. So what you could do, Sean, is you see in like the first part where we had this equation here. Let me highlight it.
So essentially just go back and plug in the roots you solved for into that equation there.
Yeah, and if it's 0, then you should be those, like, and you could do it for each root if you really wanted to. And that would work.
Okay, thank you.
So in one, I think it was in lecture 5, I believe, we talked about stress invariance. So does anyone remember what the stress invariance? Does anyone remember what the stress invariance? What you could do for how you could use the stress invariance to check your work?
It's like a property that doesn't change when you do like the stress transformation. So you can do it before and after your stress transformation to make sure you didn't mess anything up, right?
That's correct, Greg. That's absolutely correct. So So what the stress invariants are, so we have, so in this is our equation for finding our principal stresses. So if you do any stress transformation, including if you're like finding the principal stresses, the coefficients, so we'll call this first stress invariant, we'll call the second term in the parentheses, could be our second stress. The second term, come on. The second term would be our second stress invariant. And then this third term would be our third stress invariant. Okay, so we already solved for those above. So from the original state of stress, our I1 was equal to 20. Our I2 was equal to minus 500. Okay, and then our third principal stress, our third stress invariant was equal to 6,000, or it's equal to minus 6,000. Okay. All right, so those are our three principal stresses there, or sorry, our three stress strain invariants. So what we could do is our new state of stress that we have is defined by our principal stresses. So our new principal stress, our state of stress is going to be equal to this, right? So for our principal stress, on the plane of our principal stresses, or on our principal planes, we know that our stress matrix is equal to this. All right, so there's no shear stresses on for this on the plane of all the principal stresses. Okay, so because of this, we can plug in these terms, all right, into this equation here. So this is equal to sigma x, sigma y, sigma z, tau x, y, tau zx, tau y, z, and same thing on the other side of the equation. So we're just going to plug in all these terms into that equation. All right. So if we plug these terms into this equation, I'll call, so the first equation, or first term, is for the first stress invariant would just be equal to the sum of all the normal stresses. So we would just have 30 plus 10 minus 20. So that's also equal to 20. So I1 is equal to I1 prime. That's good. So I2 prime would be equal to the product of our three normal stresses and the squares of all of our shear stresses. Since our shear stresses are all 0 on our principal strain, we only have to worry about the first three terms. So the first three terms would be 30 times 10. The second term would be 10 times negative 20. And then the last term would be equal to 30 times negative 20. All right, so if we multiply all that out, we end up getting 300 minus 200 minus 600, which would be equal to minus 500. All right, that's the same as our original value, so that's good. Then the last one, I3 prime, would be equal to all the terms except the first term have a shear stress in them, so they'd be equal to 0. So it's just going to be equal to the product of our three normal stresses, or our three principal stresses. So just be 30 times 10 times minus 20, which should just be equal to minus 6,000. Right? Minus 6,000 is equal to minus 6,000. So we can show using the stress invariance that our state of stress that we transformed into from our original state of stress to our principal state of stress is equivalent to our original state. Does that make sense?
Dr. Sidebottom, I had a quick question.
Sure.
So how'd you notice that sigma P3 to the negative 20 value, and then that corresponds to sigma Z?
So you're saying, how did I do this?
Yeah, because from the equation, when you factor out, I mean, you just get three numbers. So is it just kind of highest to lowest is what you set for sigma X, Y, and Z?
Yeah. So okay. So Don, what I really should have wrote here is, so yeah, so what I did is that this is the highest principal stress, so that's why I put it in the top left. The median principal stress I put in the middle, and then the lowest principal stress I put in the bottom right. That's just the convention. So when we typically solve for our three principal stresses, we say that our first principal stress is our greatest principal stress. Our second principal stress is the median principal stress, and then our third principal stress is the lowest principal stress that we get, the smallest root.
Okay, thank you.
Okay. So like this X, Y, and Z, like this corresponds with really what this is really like the sigma 1 axis, the sigma 2, and the sigma 3. So basically we start with like an XYZ coordinate system, right? And then we have to go to get to our principal coordinate system, we'd have to rotate our coordinates in some way. So we'd have to get to some, and I'm just drawing this. This is not the actual coordinate system. I'm just trying to show you what it could look like. Is you could have your coordinate system look like this for your principal axis. So these would be your principal axes, 1, 2, and 3. So we're going from like we started it with the XYZ coordinate system, and we would be going to the the principal coordinate system, which would be like the 1, 2, 3 coordinate system, where this is like the axis of the first principal stress. This 2 would be the axis where sigma P2 acts along, and 3 would be the axis where sigma P3 acts along. Does that make sense, Don? Okay. All right. All right. So we're gonna go. So, all right. All right. So then the part C asks us to determine the direction of cosines of the principal stress with of 30 megapascals. So what we can do is we can go back here, and we can use the following equations here. To solve for those directional cosines. So it asks us in the problem to determine the directional cosines associated with the principal stress of 30 megapascals. So what we're going to do is we're going to select 2 of these equations, and we're going to use one of these equations, and we're going to plug in sigma x, tau xy, and tau zx, tau yz, and sigma y into these equations, as well as sigma p, to solve for nx, ny, and nz. Okay. So if we do that, so I'm just taking the original stress matrix that we had from the top here. Let me just copy it real quick. Right. All right. So if we do this, so the first equation would be x, which was 10 megapascals, minus sigma p, which was 30 megapascals, times nx plus tau xy, which is was 20 times ny plus tau zx, which was equal to 0, times nz would be 0, right? So if we simplify this down, we end up getting minus 20 nx plus 20 ny be equal to 0. So we would get, in this case, we would get nx be equal to ny. The second equation we have tau xy times nx. So tau xy was 20 times nx plus sigma y times minus sigma p. So sigma y was 0 minus sigma p, which was 30 times ny plus tau yz, which was equal to negative 10 radical 2 times nz would be equal to 0. So we know that nx was equal to ny, so we could simplify this down. It'd be 20 times ny minus 30 times ny plus negative 10 radical 2 and z be equal to 0. So if we solve this equation in terms of for nz, we end up getting that nz would be equal to minus radical 2 over 2 times ny. All right, and then the last thing we have is we have our final equation here. So we're going to put everything in terms of ny. So we're going to substitute in for nx. We'll say nx is going to be equal to ny. So we can say ny squared plus ny squared plus minus radical 2 over 2 ny squared needs to be equal to 1. So if we end up adding all this together, we get 2 ny squared plus should be equal to 1/2 ny squared would be equal to 1. So we would get so this ends up being ny is going to be equal to the square root of 2/5. All right, so and then we would get nx would be equal to the square root of 2/5. And then nz would be equal to the square root of 2/5 times radical 2 over negative radical 2 over 2, which would be equal to minus radical 5 over 5. So, so are there any questions about how you could use these three directional cosine equations to determine your three directional cosines?
Professor Sidebottom,
Mm-hmm.
if we were to do the
Yes, Bradley?
guessing check with MATLAB, would that work using would this be one of those situations where the I function works since we're looking for in the principal directions?
Yeah, so you could use the I function, Bradley, to determine the eigenvectors, and one of the eigenvectors should have these three values in it.
Can we use the first three equations to get the result?
Can you use just these three equations?
Yeah.
So you can't. You need to use this last equation here, because what you'd end up getting is these three equations. They're gonna have two of them are gonna be redundant. So you're gonna get two equations that are gonna be like the same. So these are only gonna, two of these equations will be unique, and then one of them will be a copy of the other one somehow.
Oh,
So
yeah.
you can't use it to solve for three unknowns, unfortunately.
Because I use first three and I get the result is 0, 0, 0.
Yeah. So because one of them is going to cancel them out. So yeah, you can't use it. You need to use this property. Okay. So what this, I guess, so okay, so we got these three values. So what does this mean, like, physically in our system? So what we're gonna do is copy this. All right. So these three principal, these are our these are our directional cosines. So what these each correspond to is, this is the same thing as the cosine of the angle between our first principal stress axis and x. This one is the same thing as the cosine of our first principal stress axis and the original y-axis. And this last one is equal to the cosine of our first principal stress with the z-axis. So these three angles would be the angle between our first principal stress, our x-axis, and our first principal stress axis. The angle between the original y-axis and our first principal stress axis. And then the third one would be the angle between our original z-axis and our first principal stress axis. Okay. So if you needed to know the angle between the original x-axis and the second principal stress axis, or the x-axis and the third principal stress axis, what you would just have to plug in the second principal stress or the third principal stress into these three equations and solve for the other three directional cosines. Okay. All right. So are there any additional questions about part C? finding the directional cosines? Okay, all right. So if there's no additional questions, we're gonna go to the next problem. Here, so we don't run out of time. The part D is not too hard. If you're interested in it, you can look at the example of the example shown in I'll call it. It's in the homework tutorial for problem 2. For homework 2, you just go to number 7. I'll go over part D. All right. So the next problem is a problem that deals with this is going to be on it deals with strength theories. So this is the lecture number 8 that we're talking about. It's covered in chapter 7 of your textbook. So what we're given is that there's a circular shaft of tensile strength, sigma yield is equal to 350 megapascals. And it's subjected to a confined state of loading defined by a bending moment of 8 kilonewton meters and a torque of 24 kilonewton meters. So we're then asked to determine the required shaft diameter in order to achieve a factor of safety of 2. And first asked to apply the maximum shear stress theory, and the second one is to apply the maximum distortional energy theory. Okay. So the first thing we need to do is we need to determine our state of stress. We're given, we have a shaft that has a bending moment being applied to it. And we have a torque that's being applied to it. So let me go the other way. Okay. All right. The moment is about the z-axis, and the torque is about the x-axis. Okay. This is our x-axis. Okay. So, so if we look at a point on our cylinder or on our rod, I'm going to draw the stress element at that point. We have the stress due to the torque, which is going to create a shear stress. Okay. Right. And then we're going to have the bending moment is going to create a normal stress along the axis. Right. All right. All right. All right. In this problem, there's no forces along the y. There's no stresses along the y-axis. Okay. All right. So in this case, we only have our normal stress and our shear stress. So our normal stress is going to be equal to the stress in bending. So for bending stress, we know it's equal to MC over I. Okay, so for a circular component, our moment was given to us as being equal to 8 kilonewton meters. C is equal to the radius of our shaft. So we can write it as the diameter over 2. And then the moment of inertia for a circular shaft is equal to pi over 64 times the diameter to the 4th. So we can repeat. So if we simplify this down, we end up getting that sigma B is equal to 8 kilonewton meters times divided by pi times 30, and there's 32 on the top, I forgot that, times the diameter cubed. Okay. So we can do the same process for the shear stress, tau xy. Okay. So tau xy is equal to, for an applied torque, is equal to TR over J. So for TR over J, we're going to have our torque was given to us as 24 kilonewton meters. Our radius would be equal to our diameter over 2. And then the polar moment of inertia is equal to pi over 32 times the diameter to the 4th. So if we simplify this down, we end up getting 16 divided by pi divided by the diameter cubed times our original torque value. Okay, so so the nice thing here, okay, is we have our given state of stress. So now that we have defined our stress and on the y-axis, along the x-axis, and we have our stress, our shear. So the next thing we need to do is we need to calculate our principal stresses as a function of our sigma x and our tau xy. So what we're trying to get towards here is, I'm going to go back to our equation sheet. All right, and we're going to look at these two cases here. All right, so the first one that we're interested in is we need to know, we're looking for is the Tau-Tresca criteria, or the maximum shear stress theory. So we're going to use this equation here to solve for the diameter. But in order to use this equation, we need to know what our principal stresses are. So to solve for our principal stresses, we're going to use our Moore circle equation for our principal stresses, our 2D equation for our principal stresses. So if we go back to equation sheet, here for 2D, we can use this equation here to solve for our principal stresses. So if we do that, we end up getting sigma x is equal to our 8 kilonewton meters times 32 times pi times the diameter cubed, and then sigma y is 0. All right, so then this would be this number divided by 2, plus or minus our square root of sigma x minus sigma y over 2, which is just the same 8 kilonewton meters times 32 over pi d cubed divided by 2 squared, plus tau xy squared. So tau x squared was equal to 16 times 24 kilonewton meters over pi d cubed. All right, so we can square that. All right. So eventually, what we end up getting from this, right, is that if we, what we end up getting is we end up getting 16 times 8 kilonewton meters over over pi d over pi d cubed plus minus the square root of 16 times pi d cubed times the square root of our moment squared, which is 8 kilonewton meters, plus our torque squared, which is 24 kilonewton meters. Okay. So if we, our first principal stress would be equal to this equation plus the first term plus the second term, and then our third principal stress would be equal to the first term minus the last term. So what we end up getting is we end up getting for our maximum shear stress is equal to sigma P1 minus sigma P3 over 2. If we evaluate all that out, what we end up getting is we end up getting 16 times radical 10 times our moment, which was 8 kilonewton meters, divided by pi d cubed. Okay. All right, there was some algebra in there, but that's what it ends up. That's what it ends up getting. We end up getting. So we know for tau Tresca that our shear stress, our maximum shear stress, has to be less than or equal to SY divided by 2N in order for our material not to fail. So you were given our SY as being equal to 350 megapascals. You were given our desired factor of safety as being 2. So we can plug in our values to solve for our diameter cubed. So if we rearrange everything, we can say that our diameter cubed would be equal to 16 times radical 10 times 8 10 to the third newton meters times 4 divided by pi divided by 350 times 10 to the 6th newtons per meter squared. This would end up giving you a value that would be in meters cubed, and you would have to take the cube root of both sides. If you do that, you would end up getting 100 and you would end up getting 0.11376 meters, or which is approximately 113.8 millimeters. So I know that I skipped some of the algebra here when I went from the when I saw the principal stresses to finding the maximum shear stress. Is there any questions about that process in order to find the diameter?
What if it is a shear bar? What do we do?
So how could you repeat that, please?
So this question is a circular road. So what if it is a square bar?
Uh-huh.
So that means the cross area is a square,
Okay.
not a circle.
So if it was a square, somehow,
Yeah.
what you would have is so like you're like, let's say you had a bending stress, or you had instead, or you had like you would still have to define what you need to do somehow for these types of problems is you would have to define your state of stress. So you'd have to define your given state of stress. So what your sigma x, your sigma y, and your tau xy would be. And then once you have your sigma x, your sigma y, and your tau xy, you can then calculate what your maximum shear stress would be. And then, so you would have to solve for sigma x, sigma y, and tau xy in terms of like the geometry that you don't know yet. Does that make sense?
Yeah. So my question is, now you find a point A. So for a square bar, what is the location of the A?
Okay, so let's say you had like a problem like okay. All right. All right, so let's say you had a square bar like that, okay? It's fixed at a wall, right? So where would the maximum stress be in this case?
Up and below.
It would be where?
Up and below have the normal stress.
Would it be here? Would it be at like the wall? So the force that's applied normal to the or perpendicular, right, would create a bending moment, right? Right. Right. And then the force would create an axial load. Right? So like if you looked at this element here, right, it would have right, so you could use so you could use so the issue with these types of problems somehow for a square beam is you have multiple variables. So you have a height, let's call that height 2c, and you have a width like b, right? So you have two variables that you need to solve for. So what you would need to do is you would have to define b. So b would have to be some known constant. And then you could determine what c would have to be in order to solve for the appropriate sigma x in order to prevent failure. Does that make sense?
Yeah, but in your original question, the road is be rotating, the square bar is not rotating.
Yeah, so you would need to use the polar moment of inertia for a square bar. Okay, which I'm pretty sure a polar moment of inertia is equal to Ix plus Iy. Right? So, and then you'd have to use R would be the distance from the centroid to the maximum point on the beam. So if you had a square, it would be like, or a square or whatever, it would be like this distance here, V or R. That makes sense. This is your cross section. Somehow.
Okay, I understand.
Okay. Yeah, so that's what you would have, that would be what you'd have to do. The tricky thing with this is that because it's non-circular, is that depending on the width of your beam or the height of your beam, R would be a function of both of those variables. So you end up getting like two. You end up getting like it's a little bit more complex because there's multiple dimensions that you have to define instead of just diameter. That makes sense?
Okay.
All right. So the last, okay, so the last part of the problem asks you to apply the maximum distortional energy theory, which is the von Mises theory. So in this case, it's this equation here. So for the von Mises theory, we have so we have because this is a case of plane stress, you can say that sigma P2 is 0. So what we end up getting is so sigma von Mises is equal to the square root of 1/2 of sigma P1 squared plus sigma P3 squared plus the difference between sigma P3 and sigma P1 squared. Right? So if we plug in all those if we plug in those values, what we end up getting is so what we end up getting here is we get would be equal to so I guess the one thing I should show here is that if we set our 8 kilonewton meters as being our moment, We set our 24 kilonewton meters as 3 times the moment. What we end up getting here is we end up getting, this equation comes down to being 16 over pi times the diameter cubed times the moment plus or minus this equation here ends up becoming a radical 10 times the moment. Okay. So if we plug in those values for our first principle stress squared, we would end up getting this equation here. So if we multiply all that out, we end up getting 449.4 times the moment squared divided by the diameter of the sixth. And then we can do the same thing for sigma P3 squared. If we do that, we would get 16 the moment times 1 minus radical 10 over pi diameter cubed squared. So we end up getting 121.3 times the moment squared over the diameter of the sixth. And then this last part of the equation here, if we multiply this out, what we end up getting is you get sigma P1 squared plus sigma P3 squared plus sigma P3 squared minus 2 times sigma P1 times sigma P3 plus sigma P1 squared. So what this ends up simplifying down to is it ends up being just the square root of sigma P1 squared plus sigma P3 squared minus sigma P1 times sigma P3. So once we, so the last term here would just be sigma P1 times sigma P3, which would be equal to 16 times the moment times pi d cubed times 1 plus radical 10 times 1 minus radical 10 squared. Okay. So what we end up getting is that if we plug all these terms in to this equation here, our sigma von Mises ends up being equal to 16 times the moment times pi d cubed, and then we get the square root of 1 plus radical 10 squared plus 1 minus radical 10 squared minus 1 plus radical 10 times 1 minus radical 10. Right. All right, and we know that when the von Mises stress is equal to the yield strength divided by n, we have failure of our component. So we know the yield strength and we know n, so we can plug it in to, we can then rearrange the equation to solve for our diameter cubed. So if we do that, we end up getting the diameter cubed is going to be equal to 16 times m times our factor of safety times the radical term divided by our yield strength. All right, so if you solve if you solve for all that, you're gonna end up getting that the diameter, if you plug everything in, is going to be equal to 109.1 So are there any questions about that process in terms of the steps that you take to solve for the either the Truska stress or the von Mises stress, and then how you can rearrange the equation to solve for the diameter? Okay.
Sidebomb, there was a question in the chat. It was why do we assume the second principal stress is sigma 3 and not sigma 2?
Okay. So why do we assume it's sigma 3, not sigma 2? Is that the question?
Yeah, why is sigma p 0 or p2 0?
Okay.
Yes.
So in this case, our stress element this is a case of plane stress. So there's no stresses like going into the page. So like so sigma z is 0. So it's like tau zx and tau yz are all 0. So because of that, we're gonna have we have a 2D case of stress. So that's why we could use this equation here to solve for our principal stresses. When we solve for this, when we solve this equation here, what we end up getting is that this term on the right-hand side here of the equation is greater than the part on the left-hand side. So when we add the part of the right-hand side to our equation, we're going to get a principal stress that's going to be positive. But when we subtract the right-hand side from the left-hand term, we're going to get a negative value of our principal stress. So because the principal stress is negative, it's going to be, and we have a 2D state of stress, we're going to have our third principal stress is going to be equal to, or sorry, our second principal stress is going to be equal to 0. So in this case, we have our three principal stresses are sigma p1, which is equal to 16 over pi diameter cubed times the moment plus radical 10 times the moment. Right. Our second principal stress is going to be 0, and then our third principal stress is going to be equal to our 16 times pi diameter cubed times the moment minus radical 10 times the moment. Now, the reason we set sigma p2 to be 0 as opposed to sigma p3 to be 0 is because we've been using this notation that our first principal stress is our greatest principal stress, our median principal stress is our sigma p2, and then our minimum, or the most negative principal stress is sigma p3. So that's why I set sigma p2 to be 0. If you had plugged in sigma p3 to be 0, you'd end up getting the same equation. But anyway, So it doesn't really matter, like in this equation, if you had done it, if you had set sigma P3 to be 0, because you would have ended up with sigma P1 minus sigma P2, and that would have been squared. Then this term would have just been sigma P2 squared, and then this term would just be sigma P1 squared. So you end up getting the same equation here, just the 2's and 3's would be flipped around, but you'd end up with the same results. I'm not sure if that's helpful, but that's why I set sigma P2 to be 0. It's based off of this notation that the first principal stress is the greatest, second principal stress is the middle principal is the median principal stress, and the third principal stress is the minimum principal stress. Thank you for asking the question. Thank you, Bradley. So, if I understand that we're past time here, I did have one additional problem that I would want to kind of go through. How could I just get like a vocal confirmation that would someone like me to continue to do the third problem?
Would you be able to also post this on YouTube as well? Or I guess it is in the recording. I
can try to post the recording on YouTube and Canvas as well. So in case someone if you missed the topic. Okay. So let's just keep going. If you need to take a little break, probably now would be a good time to do that, as we're getting set up for the last problem here. All right, so the last problem deals with the equilibrium conditions and the compatibility conditions. So we're just going to go through each of the steps here. So we're going to start with part A, which asks you to use the following equation for the stress along the x-axis for a beam with transverse loading to prove that sigma x is equal to this equation here. So what we can do is we need to determine what m of z is equal to as a function of x. So to do that, we can take a section cut at our beam at some arbitrary location x. So if we do that, take that section cut, what we end up getting is we get our beam here. And in order to keep this beam in equilibrium, we have to apply a shear force at that point, m of x, a v of x. We have to apply a moment about that point, would be mz of x. So, to keep this in equilibrium, we can simplify this. All right, to help us simplify this problem down, we can take our distributed load and we can convert it to a concentrated force at some distance xc from our section cut. So hopefully this is familiar from strength of materials. So if we sum all of our moments about x or about our section cut, and we set it equal to 0, we can then we can then solve for what mz of x is going to be. Say mz of x is going along the positive direction, and then that's going to be equal to plus our concentrated force times the moment arm x of c. Right? So we can rearrange this, and we can say that mz of x would be equal to negative concentrated force times x of c. Okay? So the question is, what is our concentrated force and what is our moment arm for a concentrated force? So F of C is the area is going to be equal to the area for our curve here. So the area of our distributed load for a triangle is going to be equal to 1/2 the base times the height. All right, so the base of our triangle is going to be equal to just the length of our section cut x. All right, and the height of our triangle is going to be equal to W times X over L. Okay? So what was, it's not very clear in our problem statement, but at X is equal to L, W of X is equal to W, right? And then at X is equal to 0, W of X is equal to 0. So, so to get W of X along the whole beam, we assume it's a line, and then we can say that the slope of that line would be equal to W over L times X. Okay? So at X is equal to L, we would get W, and at X is 0, we would just get 0. So, so that's where we can get this equation here. So our concentrated force ends up being W x squared over 2 L. And then the moment arm for a triangle, or the concentrated force, is going to act along the centroid of the area. All right, so the centroid of a triangle is like 1/3 of the base. So x of c is going to be equal to the base, which is x divided by 3. So if we plug in those values for f of c and for x of c, we end up getting minus our moment z of x is going to be equal to minus w x cubed over 6 L. Okay. All right. So we can then plug our mz of x equation into our sigma x equation. So say sigma x is equal to negative mz of x. So plug in minus wx cubed over 6L times the y times y divided by iz. All right, so if you plug all that in, we end up getting wx cubed y over 6L times iz. All right, which is what they had in the first part of part A. Okay. Are there any questions about the first part in terms of finding m of z and using it to find sigma x? Okay. There's no further questions. I'll just keep going. So for part B, we were asked to solve for tau xy and sigma y. So to do that, we can use our equilibrium equations. The first equilibrium equation we have is this. So these are on the equation sheet listed earlier in the packet. All right. So there was nothing in the problem statement that talked about body forces, so we can assume that Fx is 0. There was also, in the problem statement, we are only given two-dimensional information. There's no stresses along the z-axis, so we can assume that there's no shear stress along the z-axis. So this simplifies our equilibrium equation a little bit. So we end up getting just d tau xy dy is equal to negative d sigma x dx. So if we integrate both sides with respect to y, end up getting tau xy is equal to the partial integral of negative d sigma x dx with respect to y. So we have sigma x here, so we just have to take the derivative of it with respect to x. So if we do that, we end up getting, and we have to multiply by a negative sign, so we get minus 3w x squared y divided by 6l to the iz. We have to integrate that with respect to y. So if we do that, we end up getting tau xy being equal to minus 3wx squared y squared over 12l to the iz times plus an integration constant. Since it's a partial integral, that integration constant is going to be some unknown function of x. Okay. So, all right. So can anyone tell me what we can use to solve for our unknown function of x?
We can use boundary conditions like x is equal to.
Okay. So Manjeet, what boundary condition do we know?
So we know that when x is equal to L, Wx is equal to W.
Wx is equal to what?
Excuse me. Wx is equal to W.
That is true. But I was more looking at we've already kind of plugged W of x into we've already built it into the equation. So we're not going to use W of x. But you're absolutely correct that we do need to use a boundary condition. So I guess what I'm trying to say is there at any point in the beam, we know the value of tau xy. Right, so we know if we had a point force, right, we know that tau xy is equal to VQ over IB. Okay, so these are all constants. All right, Q is equal to the integral of y dA. So and it goes from y to the y max to the centroid. So this term Q is equal to 0 at y is equal to at tau xy is equal to c, right? So basically tau xy is equal to 0 at y is equal to plus or minus c. So that's the term we're going to use. So that was listed in, I think, lecture 7. There's a section that talks about the different boundary conditions that are common in these problems. So, so please have that reference nearby so you know what boundary conditions you could use. So in this case, we have, so we can say at tau xy at y is equal to c, we can set this equal to -3. We know that it's equal to 0. We can say the -3w x squared times c squared times 12liz plus f of x would have to be equal to 0. So we could say that f of x would be equal to 3w x squared c squared divided by 12l times iz. Okay. So that's our f of x term. You can plug it back in to rewrite our tau xy equation. So we'd end up getting 3wx squared over 12l to the iz times c squared minus y squared for tau xy. Okay. So the second problem is very similar, or second part of part B is very similar. You have to use the second equilibrium equation, which states the derivative of tau xy with respect to x plus the derivative of sigma y with respect to y plus the derivative of tau yz is equal to tau yz with respect to z plus the body force along the y direction is 0. Again, since it's a 2D problem, you can say that the derivative with respect to yz is 0, and since there's no body forces were mentioned in the problem, you can set that equal to 0. So body force equal to 0 as well. And we can solve for sigma y in terms of d tau xy dx. So it would just be equal to the partial integral with respect to x, I'm sorry, with respect to y again, of negative d tau x y with respect to x. So if we plug in our value of d tau dx with respect to dy, we can integrate this, that derivative. All right, so if we do that, we end up getting 6wx over 12l to the iz times c squared minus y squared. And then we have to multiply that by -1. All right, and we have to take the integral of that with respect to dy. So if we do that, we end up getting sigma y is going to be equal to -6wx over 12l to the iz. And then we would get c squared y minus y cubed over 3. Right, plus some unknown function of x, which we'll call g of x this time. Okay. And then, so we can use the fact that, so if we look at this beam, all right, we have a load that's being applied on the top of the beam that varies as a function of x. But on the bottom of the beam, there's no applied load at all. So this is a free surface. There should be no stress that's being applied along the y-axis. So we can say that at the y is equal to -c, we can say that the stress along the y-axis would be equal to 0. Okay. So we can use that second boundary condition to solve for g of x. All right, so we can say sigma y at x minus c would be equal to 0. So we can plug in y is equal to minus c. All right, so we end up getting 6w x over 12l to the iz times c squared times negative c minus negative c cubed, which would just be equal to minus c cubed over 3 plus g of x. All right, so what we end up getting is we get g of x would be equal to 6wx over 12l to the iz times c cubed minus c cubed over 3, which is just going to be equal to 6wx times c cubed divided by, or multiplied by 2 divided by 12 times 3 times L to the IZ. So if we do this all out, I think it ends up getting, this is 12 divided by 36, so it's the same thing as 1/3. So WX cubed divided by WX times C3 cubed divided by 3 and 3LIZ times L. Okay. So we plug that back in to our equation for sigma y. Get sigma y would be equal to sigma y, which is a function of x and y, would be equal to let's see, minus 6wx over 12l to the iz times c squared y minus w cubed over 3 plus w x c cubed over 3 iz l. Okay. All right, so that's the second part of part B. All right. So the third part, the third part asks you to determine whether parts A and B provide a compatible displacement field. Now, in order to do that, we need to use the compatibility equation. So our compatibility equation, which in this case is a 2D problem, right, is we can use this equation here. So we can use this equation here to solve for our unknown stresses, or sorry, to determine if our stress field is compatible. All right, so in order to use this equation, we need to convert our stresses, sigma x or sigma y, and our tau xy. You need to convert those to, you convert this to our you need to convert these to our epsilon x, our epsilon y, and our gamma xy. So the only way So to do that, we can use our stress strain equations. So if we go back to let's see here. So if we look at our stress strain relationships in 2D, so if we look at our stress strain relationships in 2D, all right, we can use our sigma x and our sigma y's to solve for our epsilon x, epsilon y, and gamma xy. So if we do all that, what we end up getting is for our sigma, for epsilon x, we end up getting W over 6e to the IZ times L times x cubed y plus a Poisson's ratio times x times 3c squared y minus y cubed plus 2c cubed, right? Then we get in a similar way, we can do epsilon y where we get the same coefficient up front times x times 3c squared y minus y cubed plus 2c cubed minus vx cubed y. All right, and then we get gamma xy would be equal to 2 times 1 plus the Poisson's ratio divided by the Young's modulus times wx squared over 4 iz times L times c squared minus y squared. Okay. So all we're going to do now is we're going to use this equation up top, our compatibility equation, and we're going to confirm whether or not gamma xy, epsilon x, and epsilon y are going to be, or if they're going, we're going to solve for each of these three terms. This equation, we're going to determine whether or not they will be equal for every value of x and y. So if we do that, what we end up getting is we'll get, if we take the second derivative of x, epsilon x with respect to y 2 times, what we end up getting is we get minus the Poisson's ratio of w times x times y over e to the iz times L. All right, we can do the same thing. We take the second derivative of epsilon y with respect to x squared. So if we do that, the only terms that has x that's greater than 1 is this term over here. So we end up getting minus v x y times w over e to the I z L, right? And then the last one is we have to take the derivative of gamma xy with respect to x and once and with respect to y once. So we take the partial derivative with respect to x and y of gamma xy. We end up getting negative 2 times 1 plus v over e times divided by iz divided by L times w xy. So if we plug all these into one equation, we end up getting minus 2, 1 plus the Poisson's ratio over e to the IZL times the W x, y. All right, and then on the right-hand side of the equation, we get minus VWXY over e to the IZL minus Poisson's ratio times XYW over e to the IZL. Right. So in this case, we're going to multiply both sides of the equation by e to the IZ over over L, and what we end up getting, if we do that, is we end up getting minus 2, 1 plus the Poisson's ratio, and actually we'll do divided by W as well, since that's a constant too. So we'll end up getting minus 2 times 1 plus the Poisson's ratio times XY is going to be equal to minus the minus 2 times the Poisson's ratio XY. Sorry about that. All right, so if you wanted, we can say that the negative 2's cancel out as well. And we're left with that 1 plus the Poisson's ratio times XY would have to be equal to the Poisson's ratio times XY. So we know that Poisson's ratio is a constant. So this can't be true for all values of X and Y. So the only case that this would be compatible, so because these are not equal, it's not compatible. The only time it is compatible is if, unless X or Y is equal to 0. So if X or Y is equal to 0, the equations that we develop for our stresses and strains are work, but unless they're equal to 0, there's no unless they're equal to 0, then the equations we developed are not compatible. Don't create a compatible strain field. Okay? So that concludes our this example problem. Are there any questions regarding the process or anything to in terms of the strain, in terms of the equilibrium equations or the strain and compatibility equations? I see there's about half a dozen people left. Is there any questions? Aaron and Austin or Lee, Yilong?
No, Professor.
Okay. All right. Well. All right. Well, if there's no further questions, I think I'm going to stop sharing, and I'll end the meeting. If you have any further, I'll stop the recording. But if you have any further questions or just one-on-one questions, my office hours go to 11. Okay.
Thank you, Professor.
No problem.
Thank you.